Hello guys, you're welcome back. Sometimes you deal with compound angle, such as when you have to obtain sine 75 degree. Okay? Or sometimes you have to obtain cos 75 degree, for example. Or other angles such as 105 degree, etc. etc. Okay? Or 30 degree. You have to obtain the sine or cosine or tangent, their trigonometric ratio. Okay, so you will notice that when you are to obtain these values, you are not at liberty to use the tools at your disposal, such as the unit triangle that you can use to obtain the sine, cosine, and tangent value for compound angle. We are going to talk about that at the end of this video because you will still need that. So when you are to obtain these values, it becomes a little bit difficult. But what we are about to learn right now is going to prove very useful, and you'll be able to do this. Okay? Well, don't let's waste time. Let's get right into it. Notice you notice we have basic angles to include angle 0 degree, angle 30 degree, angle 45 degree, angle 60 degree, and angle 90 degree. These are regarded as basic angles. Well, angle 30 degree, 45 and 60 degree being the most important ones. But most of the time we are not dealing with these angles, okay? But when we add up these angles or we subtract them from each other, so we can obtain other angles like the sum of these two, like the sum of these two or these two. You can pair them up in twos, okay, or in group of more than two, okay. So in that case, how do you obtain those values? And that is what we're about to learn. That is the application. So let's get right into it. We are going to make use of this figure on the board right here. You have this compound figure here. It has triangle ODE having angle A here, and another triangle OEG being an extension of the earlier that has angle B here, such that angle A and B are adjacent to one another and their sum is A plus B. And what we are going to do is we want to look for an expression or a statement that will provide us with terms that will be in relation to angle A and angle B as shown here. And we can thus use the formula to obtain the sum of the two angles. Okay? You notice here we have the line OD. Then from the line OD we have OC and we also have CD. It is true that line OC is equal to the entire line OD minus line O minus line CD. Well, I'm supposed to put line sine on top of it here, but in this video, I'm not going to be putting that so that it will be faster, okay, to save time and space. So note, make sure you put the line on top of, you put this sign on top of lines when you are representing line. Well, what can we say about OC? We have to pay attention to this. The line OG here is 1 unit, okay? Now, what can we say about OC? OC is the line down here, and we found it is the adjacent line for the triangle OCJ that has angle A plus B in it. So can we have an expression that involves line OC? Yes. We found that cos A plus B is equal to the adjacent here is OC and divided by the hypotenuse, which is 1, because the triangle OCG is involved, right? The hypotenuse is 1 divided by 1. And from here we found OC is directly equal to cos A plus B. Let us call this 1, okay? We are coming back there. Now what can we say about OD? This right here. Now OD is the whole length here, the distance from here to here. Now you will also find that this place is also 90 degrees. You will also find that OD is a part of triangle ODE that has angle A in it. Now, from an expression that involves angle A and OD is the cos A is equal to the adjacent here is OD, and divided by the hypotenuse. The hypotenuse is OA. Okay. Now, from this here, we can proceed and say OD equals the product of this OE down here and cos A. So we have OE and multiply by cos A. But I don't need to put that multiplication sign there. So let's move on. Let us call this 2. Okay. Next is what of CD? CD is the distance from here to here. Interestingly, we also found that that is also equal to from here to here, which is EF. So we know that CD is equal to EF. Okay? CD down here is equal to EF because these angles, these are perpendicular, right? They are the vertical, they are just the perpendicular, okay, from down here to up there. So such line, the line EF is equal to line CD. Now in that note, you will notice that the line EF is a part of the triangle EFG. Now can we have a statement that involves angle A and EF? Yes. EF is opposite to A. So that would be sine of A is equal to EF all over the hypotenuse. The hypotenuse is EG. Okay. Now from here, by cross multiplication, or let's say if we multiply both sides by EG, we have EF, which is the same as CD, recall, is equal to the EG and multiplied by this here, sine of A. Okay? Good. Let us call this 3. Okay? Now at this point, let us go on and put OC, this, let's put it here. We'll put this OD, this, we'll put it here, and put this here. Okay? Let's do that. So we have cos A plus B is equal to OE cos A and minus EG sine A. Okay? That's CD, right? Good. Now this is going to be very useful because all we need to do now is to obtain the OE and EG. Well, let's go back into the figure. Let's look here again. Now what is OE? OE is the distance from here to here and is found in the triangle OEG, right? Now OE is adjacent in the figure, right? In the triangle to B, to the angle B, right? So then let us see what is cos B. What is cos B? Cos B is OE, which is the adjacent there, right? Divided by the hypotenuse, which is 1 unit, right? For the triangle OGE, right? Such that from here, we found that OE simply is equal to cos B. Also, we also want to find EG, right? EG, that's the distance here. We see that that is the opposite to angle B here, right? So that is going to be sine B. That's equal to opposite, which is EG, and divided by the hypotenuse, which is 1. Okay? And we simply found that EG is equal to sine B. If I go on now and input OE equals cos B here and EG equals sine B here, I will be having cos A plus B is equal to OE, that's cos B. But let me write cos A first. Cos A multiplied by cos B, okay, and minus EG e.g. sine B. But let me put down sine A first. Sine A multiplied by e.g. sine B. This is a very useful formula for obtaining the sum of two angles. And you have two adjacent angles beside each other. Okay? And we can say, let us see the example we mentioned earlier. If you are to obtain what is cos 75 degree, okay? Cos 75 degree then is going to be equal to cos. The sum of two angles, two basic angle that will equal 75 is angle 30 degree and angle 45 degree, right? Right? And you will notice that we have an expression similar to this. You can simply go on and rewrite this in this form, such that you have this equals cos A cos B minus sine A sine B, where this is A and this is B respectively. So we have cos 30 multiplied by cos 45 degree and minus sine 30 degree multiplied by sine 45 degree. Now at this point we need something, we are going to need something that I mentioned earlier on, and that is unit triangles. Now you'll recall from unit triangle, when you have this unit triangle here, such that this line is equal to 1 unit and this line is equal to 1 unit. But from Pythagoras theorem, you can have this line, the hypotenuse equal square root of 2. Okay? And this angle definitely is going to be 45 degree, and this angle as well will be 45 degree, right? You probably recall this unit triangle. And from here, what is sine of 45 degree? You know, that simply would be equal to the opposite divided by the hypotenuse. If you rationalize it, you have that to be equal to square root of 2 divided by 2. You probably recall this method, right? So sine 45 degree is square root of 2 by 2. What of cos 45 degree? That's going to be equal to adjacent over hypotenuse, right? Which is going to be the same thing, square root of 2 divided by 2. Okay? Now, the other unit triangle that we also make use of is this one. When you have this equilateral triangle, given all the sides are 2 units, such that when the perpendicular line here divide the triangle into one unit for the line down below there. You know, in an equilateral triangle, each of the angles will be equal to 60 degree, right? And this will be 30 degree when you have the perpendicular bisector there. By Pythagoras theorem, you have this perpendicular here being square root of 3, right? You will take this line, and this line, okay? And input them into Pythagoras theorem. And from here, we have sine of 30 degree is opposite, right? 1 over hypotenuse 2, right? And what is cos 30 degree? That's also going to be equal to adjacent, right? Square root of 3 divided by 2. Now let us input that here. Let's input that here. We are not at liberty to use this on angle 74, angle 75 degree. And that is why we reduce it into this form. What is cos 30 degree? So cos 30 degree from here is 1 over 2 multiplied by cos 45 degree is square root of 2 all over 2. Yes, cos 45 degree is adjacent over, yes, square root of 2 over 2 and minus square root of sine 30 degree. Sine 30 degrees, excuse me, cos 30 degree is square root of 3 all over 2, such that sine 30 degree is equal to 1 all over 2, and sine 45 degree is equal to 1 all over square root of 2 all over 2. We would have used 1 all over square root of 2, but using 1 over square root of, we will need to rationalize later on. So this simply is equal to square root of 3 times 2 is Square root of 3 times square root of 2 is square root of 6 all over 4, and minus 1 times square root of 2 is square root of 2 all over 2 times 2, 4. And from here, this is equal to 4, and we have square root of 6 minus square root of 2. So you can see this can be very useful. And besides, we usually have some direct question that require us to do just this. So this is how the formula is obtained. Well, I'd like to see you in the next one so that we can see the second useful one. And it is from these two that other ones are obtained. See you in the next one.